nanoHUB.org.
Online simulation and more for nanotechnology.
So what I like to do is introduce you briefly to nanoHUB. So nanoHUB, we're all about modeling, simulation, and data. And we have a lot of tools on nanoHUB that can be used. I'll demonstrate a couple of them today. We're about learning and teaching, where people can integrate those tools into their curriculum. They can use it for research as well. And then some people develop software, and we have a platform for that, such that you can develop it in nanoHUB, and then you can share and publish your results with teaching materials or tools and lectures. And nanoHUB, in fact, has over 6,000 content items, so it's a library of content that we provide. We have created a new site, which runs actually inside nanoHUB. We call it ChipsHub, which is more dedicated to semiconductor education and research. And what we have in there is we have chip design tools. So currently running, we have Silvaco. For a long time, we've had running Padre and Prophet that came from Bell Labs, and we're in the process of installing Cadence and open source Synopsys, as well as open source environments. There's a lot of courses on nanoHUB, over 170 courses. So part of the stuff I'm talking about is here also in the Semiconductor Device Fundamentals course. And here we have free textbooks that are new by Lundstrom and Data and Fisher. And today what I want to talk about is really immersive learning, where you can have students explore semiconductors and functionalities and devices, etc. So we have apps for these, a variety of them. I'm going to focus on semiconductor fundamentals here. So I'm going to click on this, and I get to Abacus. And Abacus is really an assembly of tools, multiple tools. And these tools cover items such as crystal structure, band structure models, bulk semiconductors, which I'm talking about today, p-n junctions, bipolar junction transistors, MOS capacitors, and then MOSFETs. So that's what this recitation series is about. It's really geared towards faculty members who would like to integrate these tools into their classrooms. And each of these items here that I just rattled down, has a sub-page. So if I go to bulk semiconductors here, there's a couple of tools. There's a carrier statistics lab and a Drift-Diffusion-Lab. And I'm going to look at the Drift-Diffusion-Lab more intensely today, where you can do things that you might teach otherwise just in analytical expressions. So if I click on here, I'll go there. If I click on Abacus Tool Suite, either way, it takes me to a tool on nanoHUB, and specifically the Abacus tool. So it's firing up this tool right now. And as I said, Abacus is really a tool of tools. So here again is the flash page that comes up. So crystals, band structures, band structure forming, carrier statistic, Drift-Diffusion-Lab, p-n junctions, BJTs, and some older versions of these tools as well. So today what I want to focus on is this Drift-Diffusion-Lab. So here we go. So Drift-Diffusion-Lab is a way of exploring simple drift diffusion equations in a numerical fashion. This tool is actually powered by Padre, which I mentioned is a Bell Labs tool. It was developed at Bell Labs. And it really designed transistors for Bell Labs. So it's a full-fledged design tool, except here now it's encapsulated in an app where you don't have to be an utter expert of drift diffusion and the setup of details, but you can run realistic device simulations in an app. I guess I take pride in it that we really created apps in 2005 before even apps came out on the iPhone. So there's two tabs here. There's one here that says homework for Drift-Diffusion-Lab. So here are three homeworks that are listed here. If you click on them, You get tabs describing these homeworks, and you can download a PDF. And this is taken from Purdue in what we call 305 or 606. One is an undergrad, the other is a grad level class. The other one I want to highlight is this here, which is also taken from the same course. So these might be images you might be familiar with. They're roughly the analytical expressions that people can calculate. So let me go to the first one. So the first one here is really introducing the concept of drift, and let students explore that. So let's go in here. Let's look at a intrinsic silicon slab of a certain length and dope it p-type and n-type, observe some things, and then we'll ask the students later to extract some data. So let's go here to the tool, Drift-Diffusion-Lab. I'm going to apply a bias. I can look at the structure, and I think it talked about a slab of 0.1 nanometers. So we can just do 0.1 nanometer. And it suggested p-type at first. All right, p-type 10E814, so I can go in here. And I can change materials, so I can look at silicon, and I can look at germanium and gallium arsenide. I'm going to leave these parameters. I set the environment. An environment here could mean a variety of things. So temperature, and we're applying a bias. 0.2 was requested. And we can also set some details on surface recombinations, etc., which we'll play with in a little bit. So now we hit simulate, and it's running this simulation. And actually, somebody has run this before. It just retrieved it from cache, which makes some results really fast. And even if we changed it, reran it completely, this would run in probably 10, 15 seconds. So you get an IV characteristic on a slab of semiconductor, and the IV characteristic is not linear. Maybe that's the first thinking point we want to introduce to the students, and they're supposed to comment on it in their homework assignment. And so we can look at the IV characteristic. We can look at the band edge diagram under non-equilibrium. So here is the conduction band, here is the Fermi level, here is the valence band. And as I increase a voltage, you apply a voltage here, you see the quasi-Fermi level split slightly. But basically, it looks like the potential is dropping linearly, which is good, right? That's what you expect from a normal resistor or device like this. But somehow the IV is not just going up, so it's petering out. The electric field, we can look at it as well, is basically flat throughout the whole device, and it seems to be rather linear with the applied bias. So pointer, hint, something is interesting here. So now the question B was do the same thing for electrons. So we can go back in here and change the structure and make it n-type, same doping. And I'll leave the rest the same. And there we go. It's loading a cached result again. And again, here the device looks not like a linear resistor. And you can compare the two simulations. So this is n-type, this is p-type. I can switch between the results. This is a common feature we have with our tools, that you can compare scenarios. And I guess what the following question of this ask the students to do is really figure out why is this IV nonlinear, and this concept of a drift, a velocity is being introduced, so you can calculate total current and divide it by the electric field, and you should see that there is something happening in your velocities of your carriers. So that's the first starting of playing with this tool, and it gives students a little bit of intuition. Now let me clear these results here and go into something maybe a bit more interesting. That's a homework here that lets people do a lot of analytical push-ups, right? So quite typical, you say illuminate a slab homogeneously at a certain rate and then calculate the minority carrier concentrations here, assume some boundary condition here, and it walks the students through several approximations or scenarios. And just for your reference, you can, of course, set this up. And here's the whole solution set to that, right? So you can calculate all of this with differential equations, and you come up with some horrendous expressions. And then you take approximations, and you write down the approximations, and you can find these solutions on the web anywhere. And I find that people just copy these solutions, but they don't necessarily learn a whole lot. So what you can do now in this lab is actually play and get some ideas. So what we're going to do is we're going to shine light from the top, and we're going to change this, look at the structure. The structure in the assignment was suggesting some long piece of semiconductor and another basically consistently or homogeneously illuminated chunk. So what I'm going to do is I'll make this thing 0.7 nanometers long, and I'm going to make the interesting piece of the device, or the main part of the device, 0.5. And I'm going to go in here, and I can set where I like my illumination to start. So I want it to start on the left edge, and I'm going to illuminate the first 0.2 micrometers. And I'm going to assume that I don't have any surface recombination on the left. So now I've set up the experiment. I hit simulate. And let's see if that was stored already. No, see, now it's running the tool. It's assembling the results. Here I can now look at my excess carrier density. So this is my excess carrier density. I'm illuminating my slab to the left of 0.2, and I am have no light here. And this is somewhat reflective of your analytical expressions, except in your analytical expressions, you would have assumed that this to be a flat here, but there's things happening even in the illuminated section. You have a pretty strong recombination here on the surface, right? And it looks pretty linear here, right? And then it cuts down here with a boundary condition. You have, this is the electron density, this is the hole density. We are in a N-type device, and we're not hitting the system very hard with light. So now what the question asks the students to do is, this one here, assume that you have a very fast recombination on the right, and assume that your diffusion length is very small. All right, so that's probably not what we have run. We have a, what is in our material? We have pretty relatively long carrier lifetimes. So what happens if we make the carrier lifetime short into picoseconds, like this? That should make our diffusion length much, much shorter, and we can see what happens. So let's make the diffusion length much shorter. It's running the simulation right now. And since it ran the simulation this time, I want to show you what an input, aren't you happy you didn't have to write this gobbledygook like meshing and all of that? I don't think that's very helpful, by the way. So either way, so I'm going to look at my excess carriers. I should have run it the other way around, but I haven't quite done the cooking show quite right yet. So this is where the much higher, shorter lifetime, so much shorter diffusion length. That basically means as you are creating carriers here, they decay at different exponentially, and basically before they hit the end surface here, they're all decayed. So both electrons and holes. So if we make the lifetime maybe a little longer, maybe 50 here. Let's make it 50. We can change, could do it for electrons, we could do it for holes. You should see that, I'm going to do this one more time. I just cleared my results. I'm going to go back to very short lifetime, which I should have set up in the first place. So here is my result, and I'm going to look at my excess carrier density. So here's the plot I wanted to show you with a decent resolution. And what you see is that hole density and electron density are actually on separate curves. We're doing an ambipolar calculation, just not a single polar calculation. Now if and we're basically have a pretty high recombination rate on the right, and all the excess carriers are going to get killed here on the right. So we are on a PEEP-type device, so you see really rather rapid decay here, and here you begin to see sort of a linear-ish drop, but here's an exponential part to that as well. Now if I make the lifetime a little bit bigger, 10 and 10, we should see that we overall have more carriers that are minority carriers, and we should see slightly different curves because these carriers don't diffuse, don't get recombined as fast. So see, this curve is getting larger, number one, and more carriers make it to the right side or over to the right side. If we go further and make this 100, you can see where this trend is going. We can basically explore somewhat the meaning of these homework expressions, right? So where it walks you through these exponentials that are reasonable approximations, but even these approximations that you might have, they're not all that good for a realistic device. So again, here you really clearly see the difference between electrons and holes. You see as you have longer lifetimes, more of the carriers make it from the point 2 into the edge of this device. And what you can do now is also, just like being asked in this homework assignment, you can say, what if we don't have so much recombination on the surface, and let's make it, say, just 2. Instead of 10 to the 7, make it 2. And hit simulate. Then the curves should even look quite different as well. So here you basically can explore in curves with a tool of what the carriers behave, how they behave, and explore the nonlinearity of these devices. So here now, as you have a much reduced recombination rate, you actually have way more carriers arriving or being distributed through the device. They don't just all float out at the edge. So that's an interesting exploration of a comparison of what you could do in analytical expressions. But what I'd like to show next is actually something that would be much harder to do in analytical expressions. So what I'd like to do here now is look at, again, shine light from the top. I'll do it in say a 1 micron device, and we'll look at, let's just do intrinsic for now. And I'm going to set the environment up quite differently. So I have a micron long device, and I want to illuminate it, say, from 0.4 micron to 0.6 micron. So I have a central segment that I shine light on, and I want to see what happens to the device. The illumination is not very strong. Surface recombination I will allow. I'm going to set this to be, where do we go best? Yeah, let's just do 1E7. Like that. Sure that I have everything right. And I want to actually also shine light and apply a bias. Let me make sure 1 micron, 100 picosecond. Let's make that microsecond. This is fine. Okay, I think I got it all to where I want it. And let's hit simulate. So I don't think I've run this. So this will run a full IV with light. Might take a little while longer, but not a whole lot. And here you have a IV curve. And as you crank up, you can play with cranking up the illumination. You'll get a higher current. What I like to do is look at the excess carrier densities. Ooh, wait, I made a mistake. I'm sorry. Clear. I wanted a bias with light on top, structure, materials, microsecond environment, 0.4 to 0.6. That's what I wanted. I'm really sorry. Let's try this again. All right. So obviously I haven't run that one. But again, you see NV, we're applying a voltage. And if I look at the excess carrier density, I can see now how we're shining light in this area from 0.4 to 0.6, right? This is where we're going to have illumination. Here we have the electrons, here we have the holes, and we have a fast recombination on the edges. So you create carriers, and they diffuse out from the illumination region, and they're basically caught at the edges of the device. All right, but now look at this. I'm going to apply a voltage. And well, maybe I can show what does the voltage mean. So here's a band edge diagram. So I'm applying a voltage in this direction. So I would expect that electrons mostly flow to the left and holes will flow to the right. All right, so let's look at the excess carrier densities. So look at this. I can see how the distributions of carriers under bias are changed quite a bit. So the electrons are swept to the left contact, and the holes are mostly swept to the right contact. Their mobility is quite different. So there's some holes that also still diffuse into the quote-unquote in the wrong direction. And as you increase the bias, you pretty predetermine where the carriers flow, and you look at carrier distributions like this. Now you might say, well, why are these distributions so different? We are in a structure that is intrinsic. We're looking at ambipolar, so both carriers are being considered. So let's assume we make the material really cruddy, where somehow magically we can make both electron and hole mobilities the same. Or from an educational perspective, maybe we can start from the same mobilities and see what happens. So apparently this is something I haven't run before either. So it assembled the input deck and ran the whole tool set. and it's now assembling the results such that they can be displayed. The mobility got lower, the current got lower. You can compare. Again, here's the comparison. The band edge diagram under bias probably hasn't changed a whole lot. They roughly look linear like this. You can see the split in the quasi-Fermi level if you want to talk with your students about that. But basically, nothing much happened in the band edge diagram. But let's look at the excess carrier density. So now, under equal mobility models, basically electrons and holes are behaving the same in terms of their distribution on reaction of illumination with light. But now you apply this voltage again, and you can see how these distributions shift out, where the electrons go mostly to the left and the holes go mostly to the right. And remember how in a higher doping case, the distributions were kind of skewed. So here, this is the case where the mobility is high for electrons. So basically everybody can be swept to the left. And the mobility for holes is lower. So there's still some diffusion to the left side and to the right side. But not all of these carriers make it, versus the electrons basically all make it like this. And so you can really play with what happens in a real device. You can throw out some of the assumptions of equal mobilities. You can have students extract device characteristics, and you can ask what-if questions to these semiconductors. And you can play around with all these various models of shining light from the top, shining light from the left, or just applying a bias, etc. So there is one more tool that which is a simple, cute toy tool. Also has some homework assignments where you can just basically begin to explore Fermi functions, Fermi statistics, and plot them as different functions of temperature and doping and all of that. So that's another little tool that you might find useful for playing with. And it has, for silicon, it then has different doping capabilities. And then you can see the Fermi function change. You can change the temperatures. You can sweep the temperature, for example, and see how the Fermi function changes as well. And it does it in conjunction also with the doping, etc. So this is a nice little tool as well. If you have more questions, we can maybe walk through there. But I basically talked for 30 minutes, which means I should have a drink of tea or something. And maybe I should also just ask you if you have questions. So that might be a good stopping point now.
All right. One question that came in closer to the beginning of when you started presenting, someone asked, can we get the carrier distribution?
Yeah, so I think I displayed, let me go back in here. So I was here in the Drift-Diffusion-Lab. So these are the excess carrier distributions, and here are the absolute electron density, hole density, etc. You can see that as well, and you can see. I looked at the excess, so meaning the differential value from the equilibrium value. But yeah, you can see the case here where electron and hole have the same mobility. They go back down to intrinsic doping. If you go here where the mobility is different, which is like this, you can also see the absolute carrier distributions as well. And just had an idea one could do one more play here and look at what happens. Let me go in here, materials, go back to 1450, 1400, right? No, and maybe 450 here. And I don't even want to do that. What if I go in and actually make this, say, an N-type? No, let's make it a P-type device just for argument's sake. A bit higher doped. And let's look at the differences there between an intrinsic semiconductor and a P-type semiconductor, and the boundary conditions on the absolute numbers should be different. The differential numbers should be similar, I think. So that's my assumption. Haven't run it. Let me see. So here the excess carrier densities. Clear all this. So again, the excess carrier densities are quite different now due to the doping. Let me look at the absolute doping. So here you have high hole doping, very few electrons. So it's all dominated by the holes. So yes, you can look at the absolute carrier distributions as well, is the short answer.
So we have a comment in the questions. They said when I was in school, our teacher showed us a slab of N-type silicon to demo the Hall effect. It was great. I touched the slab and thought I must have an associated B field. It was just the Seebeck effect. These apps are just fantastic pedological tools.
Well, thank you for the comment. Yeah. We might have some Hall effect modeling tools as well. The one I'm demoing here does not have a magnetic field built in. Yeah, thank you.
All right, and then someone asked, what were the boundary conditions? Oh, I don't know if this was maybe back if you can remember this. What were the boundary condition used at x equals 0 and L?
I presume we maybe are talking about this case here, just to confirm. So we looked at just illumination from the left, or the case where illuminated in the middle. And maybe I need a clarification real quick in chat.
All right, if that person wants to go ahead and clarify there. In the meantime, someone asked, could one specify the light wavelength?
I don't think so. It is just rates. It just in the drift diffusion model is not a quantum model where you really have a quantum mechanical energy dependent wavelength type representation in this tool. I'm not even sure it can be done in Padre. It could be. Let me see what the input deck says. Whether it talks about a wavelength or it only talks about an excitation strength. So region 2. I don't even see right now where here's the generation piece. Yeah, it just puts a generation rate in here. So I'm not sure this tool can handle actually wavelength dependent type absorptions and generations. And I don't speak Padre per se.
Okay, someone asked, does the tool support the script-based operation? For example, does it take the script input instead of selecting inputs from the menu?
So this is the app version of Padre. If you really want to delve into Padre itself, you can go nanoHUB.org, tools, Padre. And so this tool has been used by 4,000 people, this Padre tool, and you can launch it. And then to your heart's content, you can write input decks. There's a couple of examples like a PN diode that I'll be showing, I think, next time. And you can start from existing input decks. There's also a manual that goes with it. If you are interested in more full-fledged solutions, you might also want to go to ChipsHub and click on Silvaco. And there you can get a full-fledged drift diffusion simulator that is more graphics-based for inputs, but it's still a bear to use. I would call that more for intense usage or for research / education use where you really want to teach full-fledged TCAD tools. So you can do Padre with an input language, or you can do here Silvaco with examples here. For example, you can do process simulation, device simulation. You can do all kinds of complicated stuff. So under the hood, it also has its own language, and you can run a full-fledged tool and work that way.
All right, and this could be a follow-up. It's asked by the same person that asked about the boundary conditions used at x equals 0 and L. They said, when illuminated at the middle, what were the BCs at the left and right end?
Okay, so let's go in that again. So this is the case. I just want to click through so the boundary conditions that I had chosen is rather rapid recombination on the right. So and what we saw what we saw there is the excess carrier density, right? You basically see the excess go to 0 and the absolute goes to roughly the intrinsic value. Now, if you, for example, make that rate much smaller, say 100 just on the left, for example, and simulate it, the distribution should become skewed, where not everybody is recombining at the surface, so therefore there's not everybody's emptied out, so they sort of accumulate. And here we go. So the V is here, and let's look at the excess carrier density. Interesting. So everybody makes it to the left. Is that holes and electrons? Okay. Excess. Go back in here. So basically, when there is very little recombination on the surface, you really have carriers then throughout the whole device. Let me go in here. That's interesting. But that's the boundary conditions that we had. That was the original question. And now I'm getting curious on 1E5. What happens on 1E5?
Someone asked, for the carrier distribution under voltage, is it assumed the voltage is linearly varied between the source and drain, or is it treated self-consistently?
It's treated self-consistently. So when you have, for example, different quasi-Fermi levels that are spatially dependent, the tool actually does calculate the band edges self-consistently we'll see that next week on p-n junctions, etc. So the tool by itself does it automatically. It doesn't assume a linear potential per se. The potential can come out linearly given these conditions. I saw the question on the temperature gradient. I don't not in this tool, but as I said, you can basically go in here, pre-configure what you want, and then you can copy this stuff here and download it into text onto your machine, and then you could upload it without these things. You have to chop the first column, and you can introduce a temperature gradient, I would think, or at least you should be able to, where we talk about temperatures. So you have a region that you could have at one temperature and another region at a different temperature. So Padre should be able to handle that. This app wasn't designed to do that. And this goes more towards thermoelectric devices, I presume.
How do we integrate this tool with casino software?
I'm not even sure what Casino is. Is that a learning management system?
Yeah, if the person who asked that wants to add to that, they said it runs Monte Carlo simulation on the device.
Well, that's a whole other can of worms. We have a full-fledged 2D full-band Monte Carlo simulator called MoCA. It comes from Illinois. That you can do Monte Carlo simulations. In this tool here, so this is a Monte Carlo modeling tool that is built by one of the world's experts on Monte Carlo simulation, which is Umberto Ravaioli. So they have pulled this tool together. So you can do Monte Carlo simulations. In Padre, you can have different drift diffusion models, thermal balance models, etc. But I don't think it does Monte Carlo.
All right, thanks, Gerhard. It looks like we have hit all the questions in the chat and the Q&A.
All right.